Soil bearing capacity determination is highly sensitive to the foundation type or size, the load type and inclination, soil properties, and the presence of groundwater. It is typically verified with a variety of field tests, such as the SBTN number, dynamic cone penetrometer test, and some of which of these are actually included in your site information folder when possible. But in terms of calculating this from a theoretical perspective, we'll start by discussing two terms. The ultimate bearing capacity, which is like our nominal section strength from component design. This is the unfactored or unadjusted capacity of the soil. However, with soil analyses, we will use our service loads and the ASD method. So this unadjusted capacity of the soil is reduced by a factor of safety to get our allowable bearing capacity that we then compare to our service loads. Basic course bridge design the basic bridge design course relies on the IBC section 1806, using a middle of the road value for coarse grain soil and a factor of safety of 2 to get 286 kilopascals for our ultimate bearing capacity or 143 kilopascals for allowable. And this kind of sets our default for what we've talked about throughout this section of EIA soil. But to take a deeper dive, we'll first look into defining ultimate bearing capacity. We'll start our journey with Terzaghi in 1943, whose work was then added to by Meyerhoff in 1951 to find the bearing capacity of a rectangular footing on a flat plane. This work brings us to, the full equation for this work is as follows. QU is equal to C, NC, SC, DC, IC, plus gamma, depth of the footing, NQ, SQ, DQ, IQ, plus 0.5 gamma B, or the breadth or the shortest dimension of the footing, width, N gamma, S gamma, D gamma, and I gamma. C stands for cohesion, N stands for the bearing capacity factors, capital S is the shape factors, so that is going to be based on our size of a rectangular footing, so the shape factor depends on the width and the length of a rectangular footing, whereas N, the bearing capacity factors, are going to be based on our angle of internal friction. C, our cohesion, is a property of the soil. D, it's going to be our depth factors, and I is going to be our inclination factors. And some of these factors do need to get adjusted based on the depth of the water table, but I'll talk about that in a different lecture. Especially with suspended bridges, it's unlikely that the water table is going to be very close to our foundation, but in suspension bridges, this might be the case. Now, the bearing capacity factors for Meyerhoff's equation are as follows. I won't read them out loud. They are referenced. They'll be referenced in the notes of the course. The shape factors I've also noted here. I won't read all of these equations. I won't read out any of these equations to save time, but one thing important to note for these shape factors is that they do rely on Kp, which is the coefficient of passive earth pressure, and they also rely on the dimensions of the footing. So like I said previously, we're going to have our width or breadth and our length of our footing, and our width or breadth, B, is going to be the shortest dimension. And sometimes this needs to get adjusted if there is an eccentric load on the footing. So the footing isn't loaded concentrically, it's loaded eccentrically. And we're going to use a smaller value for B and for L to account for a smaller portion of the footing that's actually picking up that load. Next are our depth factors, and then our inclination factors, where for our inclination factors, our angle alpha is going to be the angle of our load P from the vertical. And this can be neglected on almost all EIA bridge designs because the load is acting straight down with the vertical. So we can calculate all of this out and get a value for a continuous footing on a plane or rectangular footing on a plane. You may notice this is a pretty high value for bearing capacity compared to the IBC values, which are far more conservative. But there's one other step we need to take in further reducing our bearing capacity value, because we need to factor in the fact that these foundations are on a slope. And this brings us all the way to recent work by Yang in 2019 in creating a unified calculation for shallow footings near slopes. So this method requires significant interpolation between empirically derived values that depend on the slope conditions that are specific to your site. These are all presented in the supplementary research provided. And this method is not required, but it is an interesting exercise to double check the theory versus the experimental values for bearing capacity that you may receive from soil testing in the field. And ultimately, Yang is going to give us this equation, or this variable I have in green, the ultimate bearing capacity for a continuous footing on a slope. And the final step is to adjust this to get our value for a rectangular footing on a slope, which is what our foundation represents. So the rectangular footing on a slope value comes from the equation that modifies the continuous footing on the slope value, or the rectangular footing on a flat plane value, by the ratio of the continuous footing on a slope to the continuous footing on a plane. And this gives us our final equation for a theoretical ultimate bearing capacity.